So I've intentionally not given you guys notes yet. Because I'm going to ask you a question from Calculus 2. And I'll see how well you guys remember something from Calc 2.
Oh no, oh no. 5 years ago.
What does Taylor's theorem say? Well, no, don't want to. I'll let it here. What does Taylor's theorem say something about?
Continuous differentiable functions?
It says things about differentiable functions. What sort of conclusion does it make?
You can locally approximate them using polynomials to arbitrary precision.
I'll put a C infinity because infinitely differentiable. Yeah, that's the idea. It doesn't quite say that. But it fails to say that in that there exist C infinity functions that are bad. So C infinity functions that can be well approximated locally by polynomials, ones for which you conclude Taylor's theorem actually gives like some sort of convergence result. They're called analytic. And there are some bad functions, one of which appears in the homework, for which you can compute these Taylor polynomials and find that all of the Taylor polynomials are just 0, but the function itself is not 0. So you can find some bad functions. So with that out of the way, maybe I'll drop some other words. So associated to Taylor's theorem are such concepts as Taylor polynomials, which maybe you have some passing recollection of. And maybe more generally, what if I say the word Taylor series? I have some memories now that are being flagged. Okay, so the idea is you can come up with these polynomials which maybe do a good job approximating how the function is going to behave. They do, in fact, do a good job under appropriate circumstances. They do the best job that a polynomial can. And we'll get explicit control over what sort of error terms there are. So here's the theorem. So there are two different versions of Taylor's theorem. One of which I'll just call Taylor's theorem, and the other one I'll call Taylor's theorem into a main. The second one, under slightly stronger hypotheses, gives a better result. So here are, well, here we go. So Taylor's theorem in R1 says that if you take any real number a, r bigger than 0, and a function from a minus r to a plus r, which is continuous, and has its first n minus 1 derivatives all defined and continuous on that whole interval, and has its nth derivative defined at a, then there exists some error function eta from a minus r to a plus r to r, which is continuous at a, which vanishes at a, such that for everything in this domain, f of x is the same as the nth Taylor polynomial plus some error term, which is eta of x times x minus a raised to the power n. So let's even just think of what this says. I don't know, when n is equal to 1. Oh, I think that's a typo that somehow did not get fixed. There should not be an extra n there. N minus 1. So let's even think about what this says when n is equal to 1. Let's write down this polynomial when n is equal to 1. That says f of x is the same thing as our remark on convention, f upper 0 of a, that's just f of a. So if f upper n is take n derivatives, if you start with a function and I tell you don't take its derivative, then you'll just give me the same function back. That's why f upper 0 should mean f. And I'll use the convention that if I take a number raised to the 0th power, I'll set it to be equal to 1, even if it happens to be 0 to the 0, which is technically not defined. Just so I don't have to explicitly label the constant term in a polynomial. So let's see what this gives when you set n equal to 1. So you'll get the k equals 0 term, which is f of a divided by 0 factorial. So that's divided by 1 times x minus a to the 0 power, so that's 1. Plus, now the k equals 1 term, f prime of a divided by 1 factorial. So that's divided by 1 times x minus a plus eta of x times x minus a to the power 1. Does that look like a conclusion from a theorem that you recognize from somewhere before? What is it? We had a name for that theorem.
Fundamental theorem of differentiation.
It's a fundamental theorem of differentiation. Maybe I also refer to it as linear approximation. So what this Taylor's theorem is trying to do is it's taking the fundamental theorem of differentiation and saying, well, what happens if you use that philosophy, but you take the derivative n times and not just once? Nice. So as indicated in the statement above, I will denote by this the nth Taylor polynomial of a function based at some input a. What does the theorem say? The theorem, so just like how the fundamental theorem of differentiation says that the linear approximation of a function approximates that function close to a better than any linear function does. This says the same thing. It says the nth Taylor polynomial approximates this function close to a better than any degree n or lower polynomial. Because this error term vanishes to degree somehow bigger than n. So let's check this first. So the terms of this Taylor polynomial, let's think about where they come from. So in like Calc 1, the linear approximation is like the straight line which goes to the point a comma f of a and has the right derivative at a. Similarly, the like degree 2 Taylor polynomial should have the right y value at x equals a, should have the right slope at x equals a, and should have the right second derivative. In general, the nth Taylor polynomial of a function should have the right first n derivatives. And maybe we can even check that by taking some derivatives. So here's a lemma. Suppose that f is some function. Suppose that this function has first n derivatives all defined. Let's set p of x to be the nth Taylor polynomial. So that's the sum of a bunch of things that look like f. Take the kth derivative at a, divide by k factorial, multiply by x minus a raised to the kth power. Then, for every j 0 through n, the jth derivative of the Taylor polynomial is the same as the jth derivative of the function f. And I mean, let's just check this. J equals 0. So if we take the 0th derivative of the Taylor polynomial at a, what does the 0th derivative mean?
Just the function?
Just the function. So this should be the function we get by plugging in x equals a. So that'll be the sum of f upper k evaluated at a divided by k factorial times x minus a raised to the kth power. Oh, and it'll even be a minus a raised to the kth power. So the terms in that polynomial, most of them vanish, right? Because Because whenever I take x minus a, if I raise that to a power 1 or higher, then that's 0. I'm using the convention that 0 to the 0 is 1. So there's only one term that doesn't vanish, namely the term when k is not equal to 0. When k is equal to 0, so that's the same thing as the 0th derivative of f evaluated at a divided by 0 factorial times 1 plus a bunch of zeros. So at least has the right value at a. Tell me, by computing its derivative, what's p prime at a? I don't know. Let's talk through it. So the derivatives are additive, right? And they behave nicely when you multiply by a constant. And the Taylor polynomial is a sum of a bunch of constants times things that are easy to take the derivative of. So it's literally take the derivative of each term. And maybe I'll set aside the k equals 0 term first. So the k equals 0 term is constant divided by constant times x minus a to the 0 power. That's a constant. So what's the derivative of a constant function? 0. Let's look at the k equals 1 term. So the k equals 1 term will be constant multiplied by x minus a to the first power. What's the derivative of x minus a to the power 1 with respect to x? Yeah, let's say it. Yeah, it's 1. So the k equals 1 term is that constant times 1. So that's f upper 1 of a divided by, well, 1 factorial, which is just 1, times 1 plus the next term. So it'll be f upper 2 of a divided by 2 factorial. What's the derivative of x minus a squared? Times x minus a? If I'm plugging in x equals a, so that, well, those 2's cancel, but who cares? That's a 0. So this is 0. And you're noticing the terms before all vanish because you take enough derivatives to kill them. The terms after some threshold all vanish because you're plugging in x equals a. That leaves you picking up only a single term, and that single term is the corresponding derivative. So folks, believe the lemma? And well, let's make sure we all remember the chain rule. Nope, the chain rule and the power rule. What's the derivative of x minus a to any power n?
N times x minus a to the n minus 1.
Let's just remember that. So let's try to prove that lemma. So maybe we'll motivate the lemma on the board. So if you want to take, not partial derivative, if you want to take the nth derivative of a Taylor series, jth derivative, to take the derivative of this sum, you can imagine I would move that derivative inside of the sum. I would say that's a constant, so I can factor that out of each derivative. So I just need to take the derivative of this piece j times and then plug in x equals a and see what I get. So let's just do that. I mean, I'm sure you already know what the answer is going to be. But let's compute it. Let's compute the derivative of each of these x minus a to the power k's. And let's even compute the jth derivative of them. So p of x, right, that's the sum of f upper k of a divided by k factorial times x minus a raised to the power k. Let's let that be the nth Taylor polynomial of f centered at a. Let's fox any j by using the power and chain rule. So I'm going to try to take the derivative of n times. So I know how to take the derivative of x minus a to the kth power. It's on the board. This gives me k times x minus a to the power k minus 1. And I even claim that works when k is equal to 0. So I would get k equals 0, so the derivative of that constant is indeed 0 still. So do you think I could like iterate that and take more derivatives? So let's just take a few derivatives off to the side. I won't do the induction, but we'll get the formula. So if I take 2 derivatives, like that just means I need to take another derivative of that. What's the derivative of k times x minus a to the power k minus 1? Yeah. Do you think I could take another derivative of that? In fact, maybe we even notice a pattern. So if I go and just keep on taking derivatives of that, each time I reduce the power on the x minus a by 1. So if I go d by dx j times at x minus a to the k, I'll wind up with something times x minus a to the k minus j. Each time I take a derivative, I'll drop that power by 1. And then I'll wind up multiplying by something, right? I'll end up multiplying by k times k minus 1 times k minus 2, all the way down until I get not quite to k minus j, but to k minus j plus 1. Well, shoot, there's an easier way to write that. Right, that does the same job. If you were to want to use a computer to compute these things, that would be a terrible way to have a computer do it. The computer wouldn't know that, oh, you just secretly need to cancel. But notationally, it's more convenient. So writing that down, if you take all of these derivatives, and there's just these cases for emphasis, you get k factorial over j factorial no, divided by k minus j factorial. Multiplied by x minus a raised to the power k minus j. In particular, when k is equal to j, you just wind up with k factorial when k is equal to j. And if you take, well, let's see, so if you take k derivatives of this, you get down to k factorial. Are there any x's left of that? What's the derivative of a constant function? What's the derivative of 0? And so on. So the rest of the derivatives are all 0. And if you like, you guys already knew that would fall out that way. If anything, I just wanted to, not pull numbers out of nowhere and tell you if you wanted to prove that, then that's an easy induction. So now I want to actually plug in x equals a. So let's plug in x equals a. And let's look at it one case at a time. So these top cases, when 0 is less than j is less than k, what do you get when you plug in x equals a? 0. When you take the case that k is less than j and plug in x equals a, what do you get? 0. If you take 0 and plug in x equals a, you get 0. So that tells you all of the derivatives except for the one when k is equal to j. If you take k equals j, well, the derivative is k factorial. You take k factorial and plug in x equals a, you get k factorial. So this is computed now, all of the derivatives that we would want to compute of all of the ingredients in this sum. So let's write them down. So let's take the jth derivative of the nth power Taylor polynomial centered at a. So I'll take j derivatives of that. That's just what the Taylor polynomial is. Because derivatives distribute over sums, and you can pull constants out of derivatives. You get this next line. And, well, hey, look at that last line. Like, it looks complicated, but I've just computed that, and there's only one choice of j for which that's not 0, and that's when j is equal to k. So that sum simplifies a lot. So only the k equals j term appears. So the only one that I'll actually see is the jth derivative of f evaluated at a divided by j factorial times, what's the jth derivative of x minus a to the power j?
J factorial.
J factorial, I guess. So maybe it would be useful then to k is j, it doesn't matter which one I call it. Oh, hey, wait, but is that exactly the jth derivative of f evaluated at a? Awesome, that proves it. And in fact, chances are decent that when you took Calc 2, I could say anything now because presumably none of you remember what happened when you took Calc 2. You derived what the Taylor polynomial should be by just finding polynomials which have the right derivatives at that point. And then you, like, assorted some things. But with that lemma too, let's actually prove Taylor's theorem, which gives us control over how well or badly the Taylor series, Taylor's polynomial approximates this function. So let's prove Taylor's theorem. So let's let a be a real number, let r be bigger than 0, let f be defined from a minus r to a plus r, let it be continuous and have its first n derivatives all defined and continuous. Let's assume that the nth derivative at a exists. And that's all I'll assume about the nth derivative. Let's let p of x be the nth Taylor polynomial, so the sum of a bunch of things that look like f upper k evaluated at a divided by k factorial times x minus a raised to the kth power. I need to demonstrate the existence of some continuous function, well, continuous at a function, which is 0 at a, and which satisfies that for all x in the closed interval, f of x is equal to p of x plus eta times the appropriate power of x minus a. That's what I need to prove? That's what I need to come up with. I need to come up with such a function. Is that equality enough information that you can just figure out what eta has to be? Could you solve that for eta? Yeah. And you do that. You solve for eta. At least whenever x is not equal to a, so you can divide. Eta of x is just f of x minus p of x divided by x minus a to the power n. And what does eta have to be when x is equal to a?
0.
0. We require that. That's part of the conclusion. So if we're going to define an eta which satisfies the conclusion of the theorem, we better not set it to be 1 at 0 at a. So this choice of eta automatically gives us this equation. Because we used that equation and just did algebra to find eta. It already has eta of a equal to 0. The only thing that it might not have is continuity at a. But how can we check for continuity of a function at a single point?
The limit.
We could take the limit. It's an interior point to this domain. It just needs to be a limit point to use this rule. So let's just take the limit. Let's compute the limit as x approaches a of eta of x. The limit doesn't care what happens when x is equal to a. So this is the same as the limit as x approaches a of definition of eta is f of x minus p of x all over x minus a to the power n. And I claim that I'm just going to use L'Hopital's rule a bunch. So that means I better believe that the numerator and denominator both go to 0 as x goes to a. As x goes to a, what does f of x go to?
F of A.
F of a, because it's continuous. As x goes to a, what does p of x go to?
P of A.
P of a, which is the same as f of a. So the numerator goes to 0. As x goes to a, what does the denominator go to?
0.
It's 0 over 0, so we can appeal to L'Hopital's rule. So this should be the same as the limit. Take the derivative of the numerator, the derivative of the denominator, get f prime of x minus p prime of x. What's the derivative of x minus a to the power n?
And x minus A to the n minus 1.
Yeah. And now let's look at it again. As x goes to a, f prime of x goes to f prime of a by the continuity assumption. I guess as long as n is bigger than 1. P prime of x converges to p prime of a. It's a polynomial. So what does the numerator of this thing converge to? What does the denominator converge to? So we can appeal to L'Hopital's rule again. And I'll do one more explicitly, and then you guys will see a pattern, I think. So it looks like when we apply L'Hopital's rule twice, we have the double derivative of both things in the numerator. You have n times n minus 1, and we did it 2 times, only got down to n minus 1, times x minus a to the n minus 2 when we applied L'Hopital's rule 2 times. So what should we get when we apply L'Hopital's rule k times?
The case derivative of f minus the case derivative of p, and then over like n factorial over what we're taking it k times, you said? Over n minus k factorial?
Yeah, so we'll do it k times. Yeah, so I guess n factorial. Well, it will be n times n minus 1 times n minus 2 times n minus 3 all the way down to n minus k, but not quite there, n minus k plus 1, which is the same as what you said.
Okay.
And maybe I'll write that on the right here. So what you would intuitively want to have right there would be n times n minus 1 times n minus 2 all the way down to not quite n minus k, only down to n minus k plus 1. But hey, that's the same thing as n factorial, so that would be like n times n minus 1 times n minus 2 all the way down to 1. That's too many things, so we'll divide by the things that we needed to not appear. Fair enough? And notice there's this condition that k is less than n. At some point I'm not going to be able to apply L'Hopital's rule anymore. If I can just keep on applying L'Hopital's rule forever, I'll still need to stop eventually. But let's apply L'Hopital's rule as many times as we can. Let's apply it n times. So if I apply it, let's just imagine I did use this one to get it down to n minus 1 times. Then I would have the n minus 1 derivative of that, the n minus 1 derivative of p. Do those both converge to the same value as x approaches a? Yeah, because the n minus 1 derivative of that is continuous. And this is a Taylor polynomial. So the limit as x approaches a of f upper n of x minus p upper n of x, x minus a to the power n minus k, divided by x minus a to the power n minus n. Oh, son of a diddly. Well, this is just drawing right now, isn't it?
Yeah.
N minus
What should actually be in? It should be n factorial divided by.
N minus k.
N is minus k factorial.
And so now here I have n factorial divided by n minus n factorial. Okay, that's just n factorial. So now let's see if we can apply L'Hopital's rule again. As x approaches a, what does f upper n of x approach?
F upper n of a.
F upper n of a. I assume that f upper n is continuous at a. What about p upper n? What does that converge to?
P upper n of a.
P upper n of a, are those two the same?
Yeah.
Cool. So the numerator converges to 0. That's one of the things we need to apply L'Hopital's rule. What's x minus a to the power n minus n?
1.
So the denominator is just n factorial. So what does the denominator converge to? N factorial. N factorial converges to n factorial as x goes to n. Oh, well, wait, then I don't even want to apply L'Hopital's rule again, do I? I can just take the limit. So this will now be the limit. Well, that goes away. The limit goes away. That's f upper n of a minus p upper n of a divided by n factorial. But f upper n of a and p upper n of a are the same. So what's the numerator? What is that? 0. So this has just explained why the limit as x approaches a of eta of x is 0. But what was eta of a?
0.
By assumption. Does this mean that eta is continuous at a?
Yeah.
That was the only other thing we needed. So here's the conclusion, and what this says is even if the Taylor polynomials don't do a good job, whatever that means, approximating a function, they do as good a job as any polynomial of degree up to n does. You can set functions that just aren't well approximated by polynomials. And there's an example of that in the notes. Nope, not the notes, another one. So there's one version of Taylor's theorem. Here's another version of Taylor's theorem which has a slightly stronger hypothesis and will give us a slightly better result. Oh, there's a typo. That power on b minus a was wrong. It's wrong in what you have in front of you. So let's let a be a real number, r be bigger than 0. Let's let f be a continuous function and have its first n plus 1 derivatives all defined and all continuous. Then, for every b in that interval, there's some c between a and b, such that f of b is the same as the nth Taylor polynomial, plus this error term, which is of the form, the n plus 1th derivative of f evaluated at c, divided by n plus 1 factorial, times b minus a to the power n plus 1. And maybe in order to see what this is generalizing, because this is like some theorem just strengthened to apply to higher derivatives. Let's see what happens when we set n equals 0. Let's see what this gives. So let's see, when we try n equals 0, let's see what we get. We'll get f of b is equal to, well, this only has the k equals 0 term. F of a times n plus 1, so that's the derivative, plus f prime of c divided by 1 factorial, which is 1, times b minus a. What theorem does that look like, the conclusion form? The mean value theorem. So this is like a higher order version of the mean value theorem. So again, let's go through and write down the proof. And the proof will be motivated in many ways by how the mean value theorem went. Although, interestingly enough, I'll need to appeal to ideas like taking antiderivatives. So there will be some integration that happens in this particular packet. So to people, like, I also want to apologize for the ordering. Like this, like there's no multivariable calculus, multivariable analysis happening here. This is all one variable stuff. So this really should have gone a few weeks before we introduced our. And next time I teach the class, that will happen. I can say that to you because you'll never find out.
What would be the average of years between this class being taught? Since the average is just one data point.
This is, I think, my 6th year here.
Okay.
Last time I ran was my 1st year here.
Okay.
Jonah might
still be here.
4 years because it's a graduation requirement, right?
Yeah, so I think that it's run as like directed studies in the meantime. So. Okay, but let's prove the thing. So let's let p of x be the nth Taylor polynomial. So there is actually an intentional reason why I'm leaving all of the statements of what the Taylor polynomial is blank, with the desire being that you guys now have to write it repeatedly. So by the end of this hour, you'll have what the Taylor polynomials are really, I guess, beaten into you. And let's also include all the assumptions. Let a and r be bigger than 0. Let's let f on a minus r to a plus r be continuous and have all of its derivatives continuous. Have its first n plus 1 derivatives all continuous. Let's let p of x be the nth Taylor polynomial. So the proof will be complete as soon as I can show that there exists some c which satisfies the equation in the theorem statement. So as soon as I can find some c for which f of b is the same as p of b plus this error term. So I need to find some c for which this error term is the same as f of b minus p of b. So f of b minus p of b needs to be the same thing as f upper n plus 1 of c divided by n plus 1 factorial times b minus a to the power n plus 1. And wait, so we're analysts here. And this is a continuous function. How do we prove that equations involving continuous functions have solutions? What's one way of doing that?
Intermediate value.
An appeal to the intermediate value. If we can show that this is bigger, this equality and inequality going this way somewhere, and an inequality going that way somewhere, we'll be done. So that's what I'll try to do. First, maybe I'll do some simplification. I'll get the that term on its own. So that's f of b minus f of a divided by b minus a to the n plus 1th power times n plus 1 factorial is the same thing as f upper n plus 1 of c. And maybe instead of appealing directly to the IVT, I'll appeal to like the contrapositive of the IVT. If that equation has no solution, then either this is always bigger than or this is always less than. So either for absolutely every x between a and b, f of b minus f of a all over b minus a to the power n plus 1 times n plus 1 factorial is less than f upper n plus 1 of x, or the same thing but with the inequality going the other way. And notice, that's not the same thing as for all x in between a and b, this happens or this happens. It's the same thing for each x value. So we've made our assumption for the sake of contradiction. That assumption implies that either this is true or that is true. Do you think either way we'll get a pretty similar looking contradiction? In fact, I'll assume that that's the one that happens because that's the equation that I've done. And I'll also assume that a is less than b so that I can write the interval from a to b as an interval and the integral from a to b as an integral from a to b. Otherwise, the a's and b's would all just be in the opposite order and the proof would be the same. So it really is rho log. So let's see what we can do. Let's integrate both sides of this as some variable t runs from a up to x. So that's the integral of f of b minus f of a all over b minus a to the n plus 1 times n plus 1 factorial. And you know what? Like that's going to get, like that's just a constant, right? That constant will be called k from here on. It's bad form to introduce the name of a constant like that midway through it, but that is less than the integral of f upper n plus 1 of t dt, where t runs from a to x. So let's anti-differentiate both sides and see what we get. What's the integral of a constant?
Constant times x.
Well, constant times the length of the interval. So maybe we can simplify this by setting a to be 0. So that'll be, let's color code a little bit. That constant k times x minus a. How do you compute the antiderivative of a derivative?
Just take the original function.
Yeah, you appeal to the fundamental theorem. So what's an antiderivative for f upper n plus 1?
F upper n.
F upper n. So this will be f upper n evaluated at endpoints. And since all of these functions are continuous, a strict inequality of the functions passes to a strict inequality after you integrate. Let's integrate again. And maybe because on the one hand, I'm far enough along that I want to be able to finish the proof, but not so far along that I can be slow and pull that off. Maybe I'll jump straight down to here. What's the antiderivative of x minus a?
X minus a squared over 2 factorial.
Yep, x minus a to the power 2 divided by 2 factorial, which happens to be 2, but maybe it's good to put the factorial there because it'll go there soon. Well, actually, no, I don't want to put it there yet. It is the same as there being a 2 factorial there. What about on the other side? Well, maybe I will write f upper n of x. Do you know an antiderivative? Oh, that should be f upper n of t. Because t is the thing that's varying now. F upper n of t is, do you know an antiderivative for that?
N minus 1 of 2.
F upper n minus 1. If I take the derivative of f upper n minus 1, I get f upper n. So I'll take that, I'll evaluate it endpoints. F upper n minus 1 of a, that's a constant. What's an antiderivative for a constant?
That thing times the length of the interval.
That thing times the length of the interval. Yeah, so I guess I shouldn't be saying what's an antiderivative. What is this definite integral? Minus f upper n at a times x minus a. Cool, cool. Let's integrate again. And my plan is to do this enough times that I can recognize what the right and left-hand side are for an arbitrary k, and then figure out how many times I need to do that to get a contradiction. So integrating this again, I'll get that same k times x minus a cubed now divided by 2 times 3. Now that's the same thing as 3 factorial. That should be strictly less than f upper n minus 2 of x minus f upper n minus 2 of a minus f upper n minus 1 of a. That's a constant, so I know how to integrate that. F upper n minus 1 of a times x minus a minus f upper n times x minus a squared over 2, and maybe I'll even put the factorial there. No, I won't yet. No, I will. So, right, so what I'm going to do is I'm going to integrate more times. But before I integrate more times, I'm going to impose summation notation on the thing on the right-hand side of the inequality, because it looks like it's getting big. And there's a pattern amongst the terms. Like, you look at the things that have the a's in them, it looks like there's some pattern developing. So on this side, I see k times x minus a cubed. And so this is after integrating 3 times over 3 factorial. On the other side, I see f upper n minus 2 of x minus, and then there's a sum. And I think I'll try to index this sum on what the exponent on top of the x minus a is. So it looks like this index will go 0, 1, 2. And let's see, so how many derivatives do I take of k each time? Well, I take n minus 2 plus 0 of them, n minus 2 plus 1, n minus 2 plus 2. I multiply that by x minus a to the k, that's why I picked k to be indexed that way, divided by k factorial. Oh, and yeah, I'm not going to finish. In general, let's integrate k times, and I think we'll see a pattern. When we integrate it 3 times, we'll end up with a 3 in the exponent and a 3 factorial in the denominator. K times x minus a to the jth power divided by j factorial. Oh, god damn it. This k is not the same as that k. But I don't want to change the k in either of them. There, now this k is uppercase. Of f upper. So when we took 3 derivatives, we wound up with n minus 2. So after we take j derivatives, we'll end up with n plus 1 minus j. Minus the sum from k equals 0 all the way up to j of
j minus 1.
Yep. Of f upper n. So right here, when it was j was 2, it was n minus 2. So I'll go n plus 1 minus j plus k, evaluated at a, times x minus a to the kth power divided by k factorial. And I'm at time, so we will come back to this on Wednesday. We're almost completely done with it. If you like, I want to just have you imagine what happens when you take this derivative, when you apply this integral n plus 1 times. You'll have that. Let me jump. This will just become f of x. This will become a sum of a bunch of powers. When j is n plus 1, that will just cancel. It'll just be the kth derivative at a times some powers of x minus a divided by k factor k. That's the Taylor polynomial. So the conclusion will be that this constant times some stuff will be the same as the difference between the function and the Taylor polynomial. The act of then plugging in x equals b will give a contradiction. And remembering what this constant k is. The contradiction will then be f of b is less than f of b, which is a contradiction. So
then the grandeur would be a correlate to this.
Ooh, and do you guys remember what uniform convergence of sequences of functions mean? So, yeah, that's what notes are for, and the definition is recalled in the homework. The homework will have you. Right. So what should uniform functions be analytical? It means that this function is like well approximated by its Taylor series. Where well approximated means the sequence of Taylor polynomials converges uniformly to the function on some interval. You'll prove some things about such things. Nice. Cool. So remind me next time when we will finish this proof. No, you guys can probably figure out the proof from here.
This explanation like you actually like Taylor series. Well, I hated them in high school. I was just like,